Okay, so for part 3 of 6-1 notes, picking up here where we left off. So again, the key concept of finding the total linear acceleration. Don't forget you have to find the tangential and the centripetal, and then find the resultant between the two. Alright, so then the final question I threw in down here on the slide, what do we know about the total linear acceleration if an object is in uniform circular motion? Right. So again, what's this concept of uniform circular motion tell me? Well, it tells me that the angular velocity is constant. And so what does that tell us? Well, if the angular velocity is constant, what's that tell me about the angular acceleration? What's that tell me about alpha? Well, if the angular velocity is constant, that tells me I don't have any angular acceleration. And therefore, since tangential acceleration equals the radius times angular acceleration, if my angular acceleration is 0, then my tangential acceleration has to be 0 as well. Right? So make sure that kind of makes sense. So what does that then tell us about the total linear acceleration? Well, if it's in uniform circular motion, the total linear acceleration would be equal to the centripetal acceleration. Now we still have to again have that centripetal acceleration, right? So don't forget about it. But in this case, if I'm not accelerating angularly, then I don't have any tangential acceleration. So these two are just equal, right? The linear comes only from centripetal acceleration. So then the last thing I want to get into before we do the examples, and this isn't anything terribly difficult, we've actually again seen these both this year and last year, but the last thing that I do want to make sure you're comfortable with is the fact that we have angular kinematics in the exact same relationships that we have linear kinematics. And what I mean by that is we know we have VOTAT, right? We know we have the initial velocity plus the acceleration times time equals the final velocity. Well, what's the angular equivalent of this equation? Well, the angular equivalent, right, what is the angular representation of velocity? Well, it's the angular velocity would equal the initial angular velocity plus alpha times the time, right? So just like I have this equation for linear kinematics, I have the exact same thing for angular kinematics. So what about delta x equals v sub 0 t plus 1/2 at squared, right? What's the equivalent of that? So cleaning that up a little bit there. But anyway, what's the equivalent of this equation? Well, again, what's representing my change in displacement? Be my change in radians, my change in angular displacement, theta, would be equal to my initial angular velocity times the time plus 1/2 times, again, alpha instead of a, and then t squared. And then the last big equation we have kinematics is v squared equals v sub 0 squared plus 2a delta x. And so make sure you're comfortable then converting that to the omega squared equals the initial omega squared plus 2 alpha and then delta theta. Right, probably the toughest one to remember is that theta represents our x. But anyway, these three equations we do have to work with. We definitely can use these anytime that the acceleration is constant. So anytime we have a constant angular acceleration, we can use these equations. So we will see those pop up in a few of our remaining examples. Just make sure you're comfortable with where these come from and how to get these on your own. So then example 5, I would obviously encourage you guys to pause if you need to and try this on your own. They ask us to rank the centripetal accelerations of the following, right? So we know centripetal acceleration equals v squared over r. So again, pause this, try it for a second on your own, and then I'll write the answers down here in just a moment. But if you hopefully look these over and then go through them. But anyway, okay, so they ask us to do from the largest to the smallest. Well, the object here with the greatest acceleration is going to be the one with the highest velocity and the smallest radius, right? The higher the velocity, the smaller the radius, the higher the acceleration. So then the acceleration of object B is going to be the greatest. The one that has the next highest kind of set of those, if you will, would be the acceleration of object E, which would be greater than, and then we have two of those that are equal there. We'd have object A and object C, which both have the exact same acceleration, which makes sense. They're the same diagram except reversed. And then finally, D would be the smallest acceleration, has the biggest radius and the smallest velocity for that larger radius. So anyway, hopefully you weren't having too much trouble getting these, and hopefully you took a moment to try that on your own, but that is the correct order for our acceleration. Example 6, I'm really not going to spend a whole lot of time on at all. They ask us to draw the angular acceleration versus time. Again, they give us position versus time. All we have to do is realize that the acceleration is going to equal the slope of that graph. The angular acceleration is going to equal the slope of that graph. So it's going to start with a positive angular acceleration. It's going to have a 0 acceleration here in the middle, and then a negative angular acceleration afterwards. Right? So our graph, if we were doing acceleration versus time, our graph would look something more or less like this. I'd start with a constant positive acceleration for a few seconds, then I'm down here at 0 for actually quite a long time, so probably not big enough there on the graph. And then finally, I have a very steep negative acceleration for the remaining time. But anyway, hopefully this example would be pretty easy to work. Okay, so example 7 here is one of the examples where it will be helpful to remember our angular kinematics equations. So just a little bit of a tip off there as we go through. But anyway, they give us the diameter, so we know the radius would be 0.15 meters. They give us the velocities here in RPM, which again is revolutions per minute. So it's spun at 150 RPM, it slows down to 60 RPM over an interval of 5 seconds. How many revolutions does it make during that interval? So we're looking for theta, right? We're looking for how many revolutions does it make. That's what we're aiming for. Now standard convention here, standard conversions would say that we take our 150 RPM, again revolutions per minute, and we would convert that to radians per second. In this case, however, the question actually asks us how many revolutions does the ball make. So rather than converting it to radians per second, I'm actually going to just find how many revolutions per second does it make. And so in other words, I'm just going to convert minutes to seconds. So the only change I'm making there is my minutes to seconds. So 150 divided by 60 is 2.5 revolutions per second. So my initial angular velocity is 2.5 revolutions per second. My final angular velocity, again just doing the same thing, 60, and then converting to seconds, right? 1 minute to seconds, and I get 1 revolution per second. So I know my final angular velocity is 1 revolution per second, and they told me the time is 5 seconds. So this would be something where I hope most of us start thinking again kinematics. I've got 3 pieces of information. I can really find whatever else I may want. And in this case, we're looking for the number of revolutions. We're looking for theta. So the first thing we'd have to do is we would have to go through finding our acceleration. Right? So using kinematics, I've got the final velocity, I've got the initial velocity, I've got the time. I can use WOTAT, if you will. Right? I can use my final velocity equals my initial velocity plus alpha t. I know the final velocity is 1. I know my initial one is 2.5 revolutions per second. And then I've got I'm looking for my acceleration, but I know my time is 5 seconds. So as long as these are in per seconds, I'm okay to use 5 seconds. Now again, if these units were something different than per seconds, I'd run into an issue. And you guys could obviously certainly convert these to radians per second as well, and then just convert back for your final answer. But anyway, solving this out, right, so I get negative 1.5 and then divided by 5. So my acceleration is negative 0.3 radians per second, excuse me, revolutions per second squared. So revolutions per second squared. So I've got my acceleration, and then I'm looking for my displacement. So if I'm looking for my displacement, again, delta theta, I'm probably going to be using this equation, although at this point you could use any of the equations you so desire. Since we've got all of the other information, I'm going to go ahead and use this one though because it's already solved for theta. So again, my initial angular velocity was 2.5 revolutions per second, the time of 5 seconds, plus 1/2 negative 0.3, and it is very important we keep that negative, and then my time squared. Right, so at this point it's just a matter of calculating that. So I just need to calculate those numbers, and I get about 8.75, actually I think it's exactly 8.75 revolutions. And because I left it in revolutions per second, I'm actually done right there. If you had used radians per second, as again probably standard practice would suggest, right, if you had used radians per second, just make sure you then convert your final answer from radians to revolutions by dividing by 2 pi. But anyway, hopefully this question, question 7 here, wasn't too bad once we actually used our kinematics to help us out. Right, so a good chance to review what we've hopefully already pretty comfortable with. Okay, so example 8 is actually a very involved question, which is why I skipped it. It will probably need its own part of the video, which I'll help you guys set up. But I'm going to go ahead and I think I'll have time here for example 9. So I'm going to do example 9 and then I'll come back to example 8 and the last part of these video notes. But anyway, so example 9, obviously a convoluted context here. You've got basically, in a simple term, you've got this wheel that spins around, so it's a spring-loaded wheel, has kind of a little cup on the wheel that you can then place a ball in. As it rotates, it then hits a point here where it launches that ball straight up. You want the ball to reach a certain height, which they call h, and you want it to hit pretty much exactly that height. So the idea here, as you're reading through it again, and I hope you do take the time to read this, but you want it to just barely hit that object that's placed up here. So you want it to just barely go that height of h. So then they ask us again, what is the correct angle, what's the correct theta that we need to launch the ball from, so that we'll just barely reach that. So again, a rather convoluted process here. But if we actually take our time with this, it's not a terrible solve. At least I hope it's not a terrible solve. If we take our time and kind of work backwards. And so what I mean by that is, in order to go this certain height, well, once it releases from the wheel, there's not really any angular motion involved with the ball anymore, right? Once it releases from the wheel, it's all linear motion. So really, this is just a standard kinematics from back early in the year. We know we'd have an initial velocity that we leave with. We can try and find that. We can try to represent that. We know we want to go a height of h. We know our acceleration would be the acceleration due to gravity, so it'd be g. And then I know that the final velocity I want up here needs to be 0, because I want it to just barely hit that point, not really hit it with any extra force. So if I look through this, I actually know 3 pieces of information in terms of linear kinematics. I know my height, my delta y, I know my acceleration, I know my final velocity, and I want to find my initial velocity to figure out how fast that needs to be launched with. Right, so that's going to be my first step. My first step again is going to be finding that initial velocity. Right, so setting it up the same way we're used to. Right, my final velocity I know is 0. I'm looking for my initial velocity in terms of the rest of this. So plus 2 times g times my change in height there, which I'll just call h. And obviously in this case it'd actually be a minus g, it'd be a negative g. But when I add that over the other side, it obviously takes care of the negative for me. So then I know the initial velocity that I need to have is the square root of 2gh. Right? That's the initial velocity that that ball needs to be launched with so that it can reach that height of h. So I've got that initial velocity. So then the question is, okay, how does this initial velocity help me with the angular stuff? Well, if this is the initial vertical velocity it would need to be launched with, isn't that going to be related to the final angular velocity that it needs to leave the wheel with, right? That's going to be related to the final angular velocity that it has at that point. And so the question becomes, what's the relationship between linear and angular velocity? Well, linear velocity equals the radius times the angular velocity. So I know that the linear velocity at that point needs to be 2gh. So then my angular velocity is just going to have to be 2gh divided by r, right? If I solve for the angular velocity, the omega here, it's just going to be the square root of 2gh divided by r. So even though it looks like a little bit of mess, and yes, it certainly does, I've at least got a representation for what my final angular velocity needs to be. So now let's start thinking in terms of our angular measurements. Well, what information do we know angular? We know that the initial angular velocity when we launch it would be 0, right? When you pull it back to that biggest angle, it's going to start at rest. We know the final angular velocity that we need is what we just found, 2gh over r. And then they defined the acceleration up there in the problem. They said the acceleration was a constant acceleration of alpha. Right, now they may not have actually called it alpha in the problem, but they did tell us at least that it was a constant angular acceleration. So I'm going to call it alpha. So I've got these measurements then to work with. Right? What am I looking for? Well, I'm looking for delta theta. So I'm probably going to be using this angular kinematics relationship. Again, I've got the final velocity, this measurement 2gh over r. I've got the initial velocity of 0, and I've got my alpha that I can all work with, and I'm solving for theta. So again, the final here, when I square it, would actually be 2gh over r squared. My initial would be 0 plus 2 alpha theta. Obviously then, when I solve for theta, I can cancel the 2 out of both sides of the equation, divide by alpha, and theta is going to equal gh over r squared alpha. Right? So as much of a mess as that may look like, if I then gave you the measurement for, we know, gravity, for height, and for alpha, and the radius of the wheel, you could find theta.